We ended previous lecture by this main result of concern that the boundary of uniformized hyperbolic filling is quasi-symmetric to the original space, and in the case of epsilon being chosen to be log alpha, the two spaces are indeed by Lipschitz. The proof is in BBS, and the construction of phi was discussed in the previous lecture as well. One thing that I want to emphasize here is that the only assumptions on X here are that X is bounded space and alpha tau have no restrictions on them, and epsilon only needs to be less than log alpha or equal to it, which covers a lot of things, including not totally bounded spaces like a Hilbert space. And a few results regarding the size and behavior of this graph, and these are found as proposition 4.6 in BBS. I believe this paper is also in free access, so you can find the original paper, not the archive one, for free online. So again, the standing assumption, just boundedness of X and stuff. The following are equivalent. They deal with the size of the graph. A. The space X is totally bounded. What this means is that for every epsilon positive, you can always find a finite epsilon net of points. So this in particular excludes Hilbert space, infinite dimensional Hilbert space, because there you have 0 and then you have infinite number of vertices with mutually distance equal 1. But if your space is not as huge, if you are a subset of Euclidean space or something, it turns out that this is equivalent to saying that each an, this collection of alpha to minus n net, is finite. Well, there's no proof really between equivalence of A and B, because that's basically the definition, and every epsilon positive is less than alpha to minus n for some of them. So that takes care of equivalence of A and B, just definition. And C says that each vertex has finite degree. Well, if you were in level n, then vertices are either to the previous generation or to the next generation or to nearby stuff, but all the generations are finite. So that means a vertex, even if it's connected to everything that could be allowed as definition, it still will be finite. And remember, I'm not saying bounded, I'm saying finite. I'm not saying there is a number bounding all the degrees. It's just one point. Every point has a finite degree, but it's not uniform over the different vertices. We'll come to that later with the metric doubling. Condition D, G is the graph is locally compact. G with the D epsilon metric being locally compact. So all of these are equivalent to one another. Part E, that G closure epsilon is compact. So far there were no restrictions over the parameters, including this epsilon parameter, but now we have this. Each of A through E implies that G epsilon closure is geodesic. It's a geodesic space. If epsilon is less than or equal to log alpha, the familiar threshold, then A through E are also equivalent to the next claim, that boundary of G is compact. This is nice because it shows us that in many situations the graph that we build isn't too wild, the degree at every point is finite, so combinatorial arguments will work without worrying about infinite cases, and that is helpful actually later for Carrasco's results, where we identify the Alford's regular conformal dimension via a combinatorial modulus. Thank you again for watching this far, and see you in next video.